start with our seminar. So it's pleasure to have Sławomir Kolasiński from Warsaw University, and he will talk about quadratic flatness and regularity for Codimension-One Varifolds with bounded anisotropic mean curvature. Please.
Okay, so thank you for the invitation. It's a pleasure to be in Princeton. Very nice place. I'm happy to be here. Okay, so let's start with the topic. So I was told not to talk too much about varifolds. So I will focus mainly on closed sets in Rn+1. So I guess those sets, everyone knows closed sets. Yeah. So this will be simple. Okay, so first I should mention maybe that I'm going to talk about my joint work with Mario Santilli from University of L'Aquila. And let us start with defining what is a anisotropic mean curvature. So first we start with considering, so maybe we start with a setup. This will be, for the whole talk, let omega be an open set in Rn+1, and we will study closed subsets or relatively closed subsets of omega, closed, and we are given also a norm. So we are given some non-Euclidean norm. We always assume that this norm is smooth, of course, outside the origin, and uniformly convex. So this is these are standing assumptions for the whole talk. And now consider a smooth hypersurface. So, hypersurface. So given a hypersurface, we can equip it with a normal vector field. So unit normal field. And having that, we define something that I call the phi normal. Someone people call it sometimes Kahn-Hoffman normal. So I denote it by nu phi of x is grad phi of nu of x or x in sigma. So this is called, I call it the phi normal. It has this property that it has this special property that if you compute the adjoint norm, you compute the distance with respect to this metric, the polar to phi of, say, x plus r mu phi of x from sigma, then you get r. So this means on the picture that if this is your hypersurface, you have a point x somewhere, and you can touch it with the, say, this is the polar ball to the phi ball, say x r. Yeah. So maybe the picture isn't just perfect. Sorry, maybe this should be like sorry. So the tangent plane is like that, and maybe the surface goes like that, and this is done. So the normal vector is here, the usual normal vector. And the center of this ball is exactly in direction. So this point is x plus r mu x. So whenever you can touch with a ball, this phi normal gives you the direction in which you can find the center of the ball.
So new phi x, you mean?
New phi, yeah, of course.
Right. I mean the different one.
The different one, yeah. So this is the usual normal, and this
And this is
direction
one the other
kind
one.
of gives you the. Okay, so now to define what is called the so the mean curvature is, you know, in differential geometry is the derivative of the normal. So here we define also the mean phi curvature vector. It's defined as the derivative of the trace. Okay, so I denote it like that, sigma x. So this will be the trace of the new phi. So this is the definition. Actually, minus. There is some kind of sign convention that I use. There is a minus here. So it's a vector. This is a number. So now I have to. What is this? This is the Euclidean normal. So the mean phi curvature vector is always normal to the surface, right? And you can easily compute that in the basis, you can compute the formula. So I can give you the formula in the basis. So it's exactly the same. Whenever, so this is a sum from 1 to n, and this is for x sigma, and given E1, En is orthonormal basis of tangent, the tangent space. This is the formula. You can see it differs from the usual. I mean, you act with the second derivative on this graph. Okay, so this actually defines the. Now we know what is a mean phi curvature vector. This definition works for smooth hypersurfaces, at least C2, right? But you can define this in a variational way. So variational definition. Variational definition is the following. So this is actually okay. So first to talk about variational definition, we need a functional. So consider the functional given by this formula. So we integrate phi of mu of x hn. So this is really called the anisotropic surface area. If sigma is a boundary of some open set, it might be called the anisotropic perimeter of a set. And if you take, say, smooth compactly supported vector field on omega and ht to be a flow of g, then you can differentiate, of course. It's functional, but you deform sigma with the flow of the vector field to differentiate, and what you get is exactly this formula. Oh, sorry. This is, I think, wrong. No, this is, no, it's okay. I forgot. You always have to multiply by this number.
Yeah, that's the density.
Yeah, there is some kind of density. Forgot about it. So now I also have to multiply it here. But there is a scalar product with the vector field. There is this density and the measure. So
Oh, but you're putting the density again there? Oh.
Yeah. So the mean curvature. Yeah, exactly. You have the density.
Right there, right. Okay. Yeah, then we have the density in there too.
So for some of you also really know what is a mean curvature vector. So I just want to remark that my sign convention is so that if you have the polar ball, say R, and sigma is the boundary of this polar ball, so the mean curvature now points always inside. So if you read papers by Francesco Maggi, it's always the opposite. Okay. So this actually, so if you know what are varifolds, you can see them. This is the first way you can also translate it to the language of varifolds, but if you don't know, you just stick with a smooth hypersurface. Okay, so now once we've defined what is a smooth hypersurface, we can define what is called NH sets. NH sets. So there is a definition. So let H be some number. A is NH set with respect to pi in omega if the following condition holds. And there is this condition given n open with a smooth boundary. Smooth boundary and mu. Now it's a normal field, unit normal field. Normal field. But inward pointing. So inside n. And if A is in the closure of n, then you have this comparison principle. Yes. So the mean curvature of this small guy, multiplied by the normal vector, the inward pointing normal vector, has to be bounded by H. And this has to be for all x in A intersect the boundary of N. So now one comment here. So what does it say? It's an NH set. Well, the point is that we want to define curvature for arbitrary closed sets. We want to do some curvature estimates for arbitrary closed sets. But for arbitrary closed sets, of course, they don't have any structure. So we define this comparison principle. Whenever you can touch with a smooth surface, then you have this estimate on the mean curvature of the smooth guy, not on the set, but on the smooth guy. So these sets, NH sets, were introduced, I think, by Brian White in his paper on area blow-up sets for sequences of varifolds. And these area blow-up sets he proved that they are actually NH sets. And then he was doing that for Euclidean norms, fine. But then there was a paper by Guido de Filippis, Antonio de Rosa, and Jonas Hirsch, where they actually introduced these NH sets also with respect to the anisotropic non-Euclidean norm. But I think
it's essentially mimicking the maximum principle.
Yeah, exactly. You have this maximum principle. And the proof of this this is the definition, but in these papers that I mentioned, they use a technique that actually you can trace back even to Allard's paper from '86. He has this maximum principle in this paper. So Yeah. Okay, so now we know what are NH sets and what are the basic, what is the utility of NH sets. So I promised not to talk too much about varifolds, but now it's a small passage about varifolds. So the theorem that we want to use is that if you have a varifold in omega, so kind of singular hypersurface, right? Singular hypersurface in omega and have this number h. And you know that the first variation is bounded by h. Okay, so this is v weighted with phi. So it's weighted like phi. Like here, right? So there is this weight somewhere, so we have to add it from here. So assuming you have a varifold which has this property, you don't assume it's rectifiable, you don't assume anything more. Then support V is an NH set with respect to phi. So these are the main examples of NH sets that are useful for me for this talk. And now we go back to closed sets. Great. So now we know. Now I want to state the main theorem of my paper with Mario. But to do that, I need some more definitions. So first, we define for A in A. Yeah. First one is always Z and R positive. Define A over R. This will be the V minus A over R. S. We define a blow up with this point with this R. And we define, moreover, the set theoretic tangent sets of A. This will be all possible lower limits. I will just explain what is this Li in a second. So we take blow up limits of this with respect to all guys or all sequences going to 0. Okay, so and where this lower limit, this limit, it's called the Painlevé-Kuratowski limit. I think it's kind of it's almost the Hausdorff limit, but it works also for non-convex sets. So it has a different name. So I'll just write what it means. Distance x to s k states. Okay, so this is called Kuratowski, Painlevé-Kuratowski of sets. It's like it's almost the Hausdorff system. It's Hausdorff. So we gather all possible blow-up limits in this sense, in this space, in this set family of sets, set 10. And now we can define what is A star. So this will be all points of A where there exists at least one blow-up limit, which is not the whole space, and not whole space. So we have a set A, and we want to kind of consider only those points where you have at least one blow-up limit, which gives you something which is not the whole space. And I believe, well, it looks like very weak condition, but well, this is what we could do. It's what we could work with. We define this set, but I don't know how for general K, I don't know what is A star, but I hope it's not. I mean, it should be like almost all of A, I think. I mean, in many cases. So this is the hope. Okay, still, I want to define another thing, one more thing. N of A is the normal bundle. So it consists of A in the closure of A, nu in the sphere, and such that there exists a positive R. So we define the normal bundle, sometimes it's called a proximal normal bundle. It consists of pairs, a point in A or a closure of A and the vector, such that you can touch this set by a ball from this direction. Okay. And I will use also this projection map. The projection onto the first coordinate. And now, having all these definitions, I can state the main theorem. The main theorem is as follows. Assume you have this number H. So I will write all the assumptions. It's relatively closed, 0, and relatively closed and H set with respect to phi. Yeah. And we assume that the Hausdorff measure restricted to the projection of the normal bundle to the first coordinate. So this set is exactly the set of points of A which can be touched by a ball. So assume this one is radon. And radon means that it's, in other words, it has locally finite H measure. This is what it is, right? And assume it has 0 Lebesgue measure and define R to be those points in A where there exists a positive R and there exists a positive vector, the unit sphere, such that you can touch from both sides. So A plus R nu from A plus R, and the distance from the other side. Okay, so this is a set. If A is here, it might be look like smart. Like might not be smooth at all, but we want to kind of.
You have a minus in the other way, right?
Minus, yeah. There is a minus here. Sorry. Okay, yeah. So we want to kind of look at this set. And the theorem says then, first of all, this R is a positive measure. A positive. So this is the open ball. The open ball. So this means that the set, this holds for all A in A, which means that, well, in particular, R must be dense in the set A. Must be dense. But it actually says more. It says that it has locally positive measure. It's a bit more. And we can prove that actually it's almost all of A star. Okay, now, so in particular, if A star equals A, which I think happen quite often, or maybe, yeah, then you see that if A star equals A, then for almost all points in A, you get these two balls touching your set. So now there will be I will talk about varifolds for, I don't know, 5 to 10 minutes. So corollary of the main theorem. Well, if you have a varifold in omega and well, H is of course like that, and you assume the first variation is bounded by H, and you assume furthermore that the support of V has locally finite measure, something that you always assume in these anisotropic problems because of lack of homogeneity. Then the main theorem applies with A equals support V. Okay, so for this kind of, in this situation, you can apply the theorem. I mean, you know that support V star, for almost all points in support V star, you can squeeze them between two balls. Right. So why is that important or maybe interesting? At least interesting. I don't know. It's so important. But so now a brief summary of known results of varifolds. So in case 5 Euclidean, in case 5 is Euclidean, we have so-called monotonicity formula for varifolds, which says that basically for almost all points, you have this bound. For V almost all X, you have this bound. This comes from monotonicity formula, where R is controlled by, I mean, for R between 0, say, and some R0, and where R0 is depending on H. Yeah? So you have this monotonicity formula, and this actually implies that almost everywhere the approximate tangent plane to your varifold equals the classical tangent plane to the support. In the lower bound, when you have an approximate notion, there is some noise of density 0 that you can forget about. But if you know that each point carries some mass with it, then you don't know that the noise cannot be there. Right? So this means that for V almost all X. So this means that your varifold is flat, basically L infinity flat at these points in small scales. And there is this theorem by Allard, 1972, the classical one, which can be stated, I will really make it oversimplified. Right? So assume L50 flatness, which is what I understand is that in small scales, you have you're close to the tangent plane, basically. Plus some, some generic conditions. And this somehow, if you have a point at which you have this flatness, and this point is kind of a generic, I don't want to state all these conditions, well, it's generic, then you have C1 alpha regularity. And this is my Allard, the classical paper of Allard. And then you have, this works for the Euclidean. Right? And if you if you change the norm to non-Euclidean, you go to the anisotropic setting, then you have a similar theorem, also by Allard, but it also assumes L-infinity flatness. Plus, well, we always assumes this, absolutely continuous respect to V, plus generic conditions. I'm always talking about the situation like here. I don't even mention that we have bounded intervals, right? So all varifolds bounded. And there is this 1986 paper by Allard, which gives you C1 alpha regular. But you see, there are some generic conditions. There is this condition which you cannot forget about, but there is this L-infinity flatness somewhere encoded. And this is non-generic. In the Euclidean setting, it was generic because of that. But in the non-Euclidean setting, here is a phi non-Euclidean, right? Non-Euclidean. For this last theorem is for phi non-Euclidean. You don't have the monotonicity formula. You don't have lower bounds on the mass points, which this allows to prove flatness at generic points, right? And so now you see, if you combine this with my theorem of Mario, you have this flatness at almost all points of A star. Okay? And this actually allows you to say that at almost all points of A star, you have C1 alpha. Almost all points of A star are C1 alpha regular. Okay, so this is the motivation for proving the main theorem.
So if you could prove that A star is, say, dense, then you would have...
Yeah, it is dense. It is dense by the theorem. It is dense. I mean, it follows from here that this implies that R is dense in A. It's dense.
But so what are you missing to conclude then exactly?
What?
So aren't you then concluding for the varifold initially that you have a dense regular set, or am I missing something?
Yes, there is a dense regular set.
Okay.
Yes.
So
yes,
then you get it as a corollary.
Yeah, that's it. We get a open dense regular set, yes. For density 1, right? For density 1.
For density 1.
For density.
For density 1, okay.
For density.
Okay, fine.
I didn't say, okay, so this theorem, of course, works for any variable, even non-active, but I mean, yeah, it has to be active. But this, if you want to apply Allard, you need the density. Yeah,
Right. I mean, then again, because of the monotonicity formula, you would actually, in the Euclidean case, because of the monotonicity formula, you would get then density irrespectively of the one assumption, right?
I didn't understand.
No, I mean, then if you just have an integral varifold, you will use the monotonicity to get
in Euclidean, yeah.
Right, in Euclidean, right? But you're obstructing to do the same. Or can you argue Bombieri style?
I don't understand the question.
So the question is, assume I give you an integral varifold, and so now I'm not telling you that the density is equal to 1 almost everywhere. Can you actually conclude that it's C1 alpha on a dense set?
No, I cannot.
Yeah.
No, I cannot. Yeah, we tried, but it's not. No. Actually, at this point, I don't remember. I can look it up. I have to recall where was it important that it was density 1? I think Allard this result, this arrow actually
is using density one.
Is using density one. I think so. I don't remember right now. Sorry. Okay. So, I mean, what we proved with Mario is this theorem, the main theorem, right? And then we noticed that, okay, it can be applied here. Just check that all these assumptions that are states like, 12 of them or something are satisfied and it applies, okay? So now I want to tell you something about the proof. A few words about the proof. The proof uses several tools. So now I want to study the structure of closed sets and the normal bundle to the closed set. So we want to define several things. We define xi will be a multi-valued map, the nearest so-called nearest point projection. So this is all y of a such that x minus a equals the distance of x to a. There might be many points like that, so it's a set. So it's a multi-valued map. We define another multi-valued map, but there will be these maps will be single-valued in many cases, in many places, say, over the distance x to a. This is defined for x with Rn plus 1 minus closure a. So this is a kind of a normal map, but it's defined everywhere outside of A, not on A, right? And we define the U and P as a unique nearest point. So this is the set of Rn plus 1, those A plus X, such that well, the counting measure, this is single valued. Yeah, single valued. So this is a set of where there is a unique nearest point to the set A, and everything is defined using the Euclidean norm. Now, actually, the whole paper we're talking about NH sets with respect to phi, but it turns out that you can do everything in the Euclidean norm, actually, and then somehow we don't need the phi norm here. So we define all these things with respect to the Euclidean norm. And there is a theorem, actually, I think it's even in Federer's curvature measures paper, that this is actually the set of differentiability points of the distance function. So this is the domain of the derivative of the distance function. And you see, the distance function is always Lipschitz continuous. So Rademacher theorem says that actually Rn is 1 x. So this is by Rademacher. Okay, and then we still find some other things. Delta A will be the subset of the normal bundle consisting of those A nu, so that there exists some R positive such that A plus R nu is a differentiability point of nu A. So it's a bit different than the usual normal bundle. A smaller set, and we define the ridge function. The ridge function is the supremum of those R for which A plus R in for which distance A plus R nu to A equals R. So this is so-called a ridge function. And I'll be using the following theorem, which is a combination of several results by Mario Santilli, proven also in my paper by me and Mario, and some of them in the paper by Mario Santilli and Daniel Hug. So, but I will just state the principal properties of these things.
Can you draw some pictures, maybe?
Pictures.
That would be useful.
Okay, so what do you want? So if you have A,
yes.
you have X, you project it onto psi of X, its nearest point. And it happens that if it's the nearest point, then you have a right angle here. If there is a tangent plane, maybe not, maybe there is no tangent plane. So this is psi of X, and if you have X, then actually nu of X is maybe on this line somewhere here. So it's just the normal vector in this direction. The U and P is the set, well, you have exactly 1 point. So if you have like a part of a signal, say, so there is just X, some Y here. So maybe the distance is always the same. So these nearest points are all these things. So this is not in U and P, but all these points here are. Okay. So this is I don't know, I don't have a picture for that. And the reach function is exactly, you know, when you have this Y, so maybe all these points are at the same distance, but they are the distance Ri. Well, if A equals, say, B plus R nu, so B nu equals R. This is the maximum how far you can get away from A, so that you have exactly 1 point there.
Are you going to use mu of A even when sigma, or even when psi of A is made of more than 1 point?
Yeah, you can do that, but I won't.
Okay, so
it's you can see that on U and P all these functions, this and this.
yeah, but are you going to use that functions outside U and P?
No, but it's easier to define it this way.
Okay,
I think it's easier to write it just.
Okay, but
so what you have to know is, okay, I mean, yeah, we're using this kind of things. And the theorem says that, first of all, this is almost all, the n tilde is almost the same as n. So it's not exactly visible, but it's a theorem. It's a theorem. I won't prove it, but I want to use it. Then if you have A nu in this n tilde A, then you can define then d nu. So this is d nu at I plus R nu. So by definition, this is differentiable at this point for some R. So take R for which this is differentiable. So this is self-adjoint, which means that it has real eigenvalues, right? So with eigenvalues chi A1 of, I call this X. So we order them this way, X, and all of them are at most 1 over, so we have a bound 1 over the distance, so they are bounded. And now we can define, well, it's a part of the theorem, but the definition is inside the theorem. Define R, AI, of A nu to be exactly this number divided by 1 minus R, AI. AI. And the theorem says that this definition makes sense. It doesn't depend on R. Okay. So this definition makes sense, and we call, sorry, not R, kappa. So kappa is what I call the principal curvatures of myself. It's defined on the normal value. And this is the way we can talk about curvature of arbitrary closed sets. Now, how much time do I have?
15 minutes?
15. 15. Okay. Great. So that's fine. So this theorem says that almost everywhere in the normal bundle you can define principal curvatures. And these principal curvatures have something to do with the mean curvature vector, of course. They must have, because otherwise.
But there's no reference to phi so far, right?
Yeah, this is the point. In this paper, in the proof, we don't use phi. I mean, we exploit this, actually, that all norms on Rn are comparable, but if they are C2, if you can touch with a Euclidean ball, then there is a smaller ball inside, because we assume phi is smooth. So you can.
So the touching condition is
the touching condition does not depend on the choice of phi, actually, as long as it's smooth. So yeah, if you can touch with this, you can touch with the other one. So it happens for some reason that we don't use phi in the proof somehow. But we use some results about NH sets with respect to phi. Okay, so having defined all these objects, I hope, yeah, they are kind of natural, but you have to define them. Now I can kind of describe the main steps of the proof. There are 4 steps, there are 4 lemmas, which give the proof of the main theorem. First lemma is the following. Assume you have a nu in this normal bundle. And A is, of course, an NH set. With respect to phi. Then you have these bound on the principal curvatures. To sum all of them, 1 to n, this at most. So this is the biggest one. And you have a bound of this type. There is some constant h plus 1 over the Ricci function. So this is the first lemma. It says that all these principal curvatures are bound. I didn't write a part of the theorem says that this is part of the theorem says that this is at least minus 1 over the Ricci function, but might be plus infinity. Plus infinity. So the theorem says that these principal curvatures are never minus infinity. There is a bound from below, but maybe they are plus infinity. But if you are an NH set, then we also have an upper bound, which involves the H. So it's like the morally, you see, you have n numbers bounded from below, and the mean, so the sum is also bounded, so all of them are bounded. Yeah, but of course, this is an extent with respect to phi. You have to do some work to prove it. Since I will think about which proof to describe, but maybe I will first state the lemma 2. I don't want to spend too much time on this proof. So assume A is not the whole the whole set omega, and all the principal curvatures are finite for almost all points, all A mu. Yeah, assume that you have this, which will be the case in case A is an LH set by lemma 1. Then you can actually prove that the set of points that can be touched by a ball has locally positive measure. Or I have to say what for A in omega, the boundary of A. Okay, the boundary is, I mean, the topological boundary. I mean, if A is a closed set, so it can have non-empty interior. So I don't want to look at the interior points, but that's why I write the boundary of A here. And are positive. Okay, so this is done basically using a Korea formula. You can disintegrate the Lebesgue measure using this. You know, it's basically MP is the whole space up to set measure 0. So you take this ball, you disintegrate the Lebesgue measure with respect to using the Korea with respect to fibers of the nearest point projection, and you have some formula, some integral over this set, and you know it's non-negative. So it must you know it's positive. And so we are getting closer. Now there is lemma 3. Lemma 3 says that if you have an NH set, if you have an NH set, where is it? Here, which has 0 measure, the Lebesgue measure, and you know that the set of points that can be touched by a ball has locally finite measure. So this is radon. Then you know then for Hn almost all A in this set, there exists an R positive and exists a new vector such that we have these two things. Okay. And how do we prove that? So maybe I can spend a few minutes talking about the proof of this. It's actually quite natural to expect, because how do you prove that? First of all, you see that this is the set of points which can be touched by a ball. So by some abstract, I mean, some other theorem says that it must be rectifiable, actually it's rectifiable, because it can be touched by balls. From one side, it's enough. If you can, the set of points where you can touch by a single ball is always rectifiable. So assume this is not true, so there is a set of positive measure when you can touch with only one ball, not two. I mean, you can touch at most 2 balls because it's Codimension-One. It's always true. But assume there is a positive, so there is a compact set, say, in this subset of this guy with positive measure, like that, so that you can touch only with one ball. You have only one normal vector. And then we do this trick that you can compute the Minkowski content of this guy. Okay. So the Minkowski content, you take, actually, we only use lower Minkowski content. You take the, we take a thickening of this guy, and you want to have 1 over 2R. And you know, for rectifiable sets, I mean, you have a lower bound, at least. But you see, now you do co-area. You take this thickening, you do co-area, you disintegrate the Lebesgue measure with respect to fibers of the nearest point projection, and you get some strange thing, like, you know, you have this K here, and you can touch it only from one side. So your co-area formula will have only kind of one side, and you divide by 1 over 2R, you will see that this actually converges to one half of this. Is 1/2 using co-area, because there is only, like, if you disintegrate it, you see only from one side. Yeah? So, and this is of course impossible because you have this bound priori. And so for almost all points, actually this is kind of more involved because to pass to the limit here, you use co-area formula. Inside the co-area formula, you have certain function which depends on the principal curvatures. Because you do co-area, you have this Jacobian somewhere. So it depends on the principal curvatures. And it only works for, you actually use that it's an NA set because you need lemma 1, which says that these guys are bounded like that. And then you can use dominated convergence theorem, because what you get from the co-area is then bounded, dominated by one function. You can pass to the limit. If you didn't have that, because for an arbitrary set, I wouldn't expect this to be true. But for an NH set, you have bounds on the principal curvatures, and then you can use dominated convergence to actually show this is true. Okay, so so this is actually, if you combine lemma 1, 2, 3, you see that you can prove more or less this theorem, but you don't get yet the last conclusion. So this is the point of lemma number 4. So lemma number 4 is the following. Lemma 4, it says, that's this. Here it is. A and NH set. Once again, of course, always with phi, yeah. And A is in A star, so there is at least no, it didn't survive. But this A star was the set of points in A where you had one blow up, which is not the full space. And then you can prove then there is a density bound 0 plus 1 over R to the N, and then we can measure B A R intersect E and A. Well, it's positive. For all A in A star, you have this bound, which actually by abstract measure theory says that this is a full measure set. Because if there was a positive measure set with, if there is a complement with positive measure, then some points would have density 0. And 1 minute. Okay, so the proof goes basically that there is a picture like that. So you have a point A somewhere here, and you know it's in A star, which means that there is a kind of a sequence of balls which do not touch your set. So you have in these balls, you don't have the set A at all. So you do a blow up, and when you do a blow up, you always get a picture like that. There is somewhere there is this point A, and if you blow up, there is always a single ball which does not contain any point of your blow up of A. And what you do, you have your A somewhere here. You do a diffeomorphism that pulls this guy inside. And since you know there is nothing here, and you pull A somewhere in this ball, there is some part which can be touched by hyperplanes locally. And then you can translate it back using the diffeomorphism so that there is a set, positive measure set, like positive density, which can be touched by balls. These hyperplanes can be translated to balls. And this is it. Okay, thank you.
Questions? So, you were raising that hand?
No.
So let me, so when you were saying that the result is limited to the fact that you're assuming the varifold has multiplicity 1.
Yes.
Can't you do the same at a point, say, if you know that the multiplicity is something and everywhere else in a neighborhood is bigger or equal, then that's something?
Yeah, we tried. Yeah, it's usual, as in the proof of art, right?
Right, as
So it doesn't come down.
or yes, exactly. I mean, so there's a problem over there that you can't, because that would give you density irrespectively of the.
Yeah, I know. Yeah, there was a problem. Now I'm trying to remember. I'm trying to remember what was the problem. Yeah, but we tried. Yeah.
Of course, there is also the other assumption that you always ask that the Hausdorff measure is fine. I mean, the Hausdorff measure.
The support is not bigger than
the
support. It's not bigger in Hausdorff measure than V actually.
Right.
So this is always because you don't have more intensity. You have to assume that.
To assume that. Which is annoying, though.
Which is of course annoying, but no one knows. Well, of course. I mean, if I could drop this assumption, I think.
If I want to drop that assumption, then the whole problem will be solved. Yes.
Yeah. So this I have to. But about the density, well, I'm sorry, but I remember we were thinking about it, but at this time I just can't recall what was the problem. I can look it up because I have to look at the paper and see what was the problem. But somehow it dropped off my mind somehow.
Okay, if there are no other questions, thanks.